Let's take a look back at some of the ideas we've discussed. First, trigonometric functions can be defined for acute angles by placing that acute angle as one of the acute angles in a right triangle, and then we can define the 6 trigonometric ratios as ratios of the side lengths of that right triangle. Importantly, there are some relationships we can talk about. There are reciprocal relationships between sine and cosecant, for example, and there are cofunction relationships between sine and cosine, among others. A second topic is the idea of solving right triangles. We had a few tools for doing this: the Pythagorean theorem, the angle sum theorem, trigonometric functions, and inverse trigonometric functions. And the idea of solving right triangles is that if we're given some information about a right triangle, we'd like to find other information. Because the angles have to add up to 180 degrees, because of the angle sum theorem, we know that whatever this acute angle is, the other one has to be 90 minus that amount. If we know 2 of the sides, we can find the third side using the Pythagorean theorem. And if we know 1 angle and 1 side, we can set up a ratio. So if we know theta, for example, and maybe we know either x or y, we can set up the tangent ratio to find the one that we don't know, the side length that we don't know. And tangent of theta, it's y over x, as displayed in the diagram. And there are kind of 2 important differences here. If we are looking for x, well, in any case, to solve the equation, I can multiply both sides by x to clear out the denominator. If we're looking for x, I then get an x times tangent, and to get x by itself, I need to divide by tangent, which gives us an answer of a kind of slightly different flavor than if we're looking for y. So if I'm trying to solve for y, again, I'm going to multiply by x, but then that leaves y all by itself, and so the solution is simply y equals x times tangent theta. And so there's kind of an important difference there. And the idea is, if we're trying to solve, if the unknown is up in the numerator, we're going to get a simpler answer. We're just multiplying through by x gives us kind of directly the answer. But if the unknown is in the denominator, if what we don't know is x, then we have an extra step to do after we multiply through by x. We have to divide by tangent. If we're given 2 side lengths but none of the angles, we can use inverse trigonometric functions to find what the angle measures should be. The process of solving right triangles can be an important part of applied problems, and related to those are some terms, angle of elevation, angle of depression, and pitch, that are helpful in setting up the diagram needed to solve those sorts of problems. A third topic that we've taken a look at, so those first 2 topics dealt with right triangles, but we can extend the trigonometric functions to angles of any size by defining the idea of an angle in standard position. And then what becomes important is the idea that we can create a right triangle by choosing some point, really any point on the terminal side, and drawing a vertical line to the x-axis from that point. Once we do that, it gives us this reference triangle, and we can define side lengths for that reference triangle based on the coordinates of the point that we chose on the terminal side. And so the side lengths, it may seem a little strange, but the side lengths can be positive or negative. And in the first quadrant, they're going to be all positive, but in other quadrants, in quadrant 2, the x-coordinate would be negative, same in quadrant 3. In quadrant 3 and 4, though, the y-coordinate will be negative. So in quadrant 3, both x and y are negative. In quadrant 4, just the y-coordinate will be negative. So we can get positive and negative values for the trigonometric ratios, but the idea of an extension is that it does match with our original definition for acute angles. So if we're between 0 and 90 degrees, we're going to get the same values that we would have just by looking at a simple right triangle. But then extending to angles that are bigger than 90 degrees or negative angles, we can use these definitions based on the reference triangle to come up with answers. So at the heart of it, in order to find exact trigonometric function values, what we need to know a point on the terminal side that has exact x and y coordinates. And so different problems will present information in different ways, but you should be able to figure out if you're requested to find an exact value, you should be able to find some point on the terminal side that has exact x and y coordinates. If what we're given is the value of theta, then to find an exact trigonometric function value, to find exact trig values, the reference angle must be either, for what we know at this point, the reference angle must be either 30 degrees, 45, or 60 degrees based on the special right triangles that we're able to find exact side lengths for. Or it could be true that theta could be a quadrantal angle. So let me talk about a couple examples related to that. So remember, the reference angle is the acute angle formed by the terminal side and the x-axis. And so in this diagram, I don't give you exactly what theta is, but we're going to say that the reference angle is 60 degrees. So theta, I guess with the blue line that's sketched out there, theta would be 240 degrees, because it would be 180 plus 60, but it could be something else. It could be anything coterminal to 240 degrees. In that case, if this reference angle, again the reference angle is between the terminal side and the x-axis, if that reference angle of 60 degrees, what that does, it forces the terminal side to be a certain shape, and it's the shape of one of our special right triangles. So if I choose a point that's 2 units away from the origin, I know that the x-coordinate is -1, and the y-coordinate of that point is negative square root of 3. So we have x is -1, y is negative square root of 3, and r is equal to 2. And so we could define any trigonometric function. In particular, we could define the cosecant function to be r over y, 2 divided by negative square root of 3, and if we rationalize the denominator, we get -2 square roots of 3 over 3. Quadrantal angles present a slightly different problem because we don't really have the opportunity to create a reference triangle. We can't really drop a vertical line or raise a vertical line to the x-axis. And so if we have a 90-degree angle, for example, we know that the terminal side would be in line with the positive y-axis, and so it's between quadrants 1 and 2. But because it's on the positive y-axis, I know that for any point on that terminal side, the x-coordinate is going to be 0, and the y-coordinate is going to be some positive number. And from that, we can, using the formula from up here, I know that r is going to have to equal that same y-coordinate. And so if we choose y equals 1, x equals 0, y equals 1, r also has to equal 1. And so, for example, sine of 90 degrees is y over x, but both of those, whatever they are, they're exactly the same. And so the ratio is going to equal 1. So this is a summary of some of the ideas that we've talked about so far in the course. I hope you enjoyed the video. Thanks for watching.